This talk addresses the possibility and extent of coseismic excitation of tsunamis from large megathrust earthquakes into back arc basins. This was mainly motivated by this year's earthquake in Oaxaca, and here we're going to take a look at the potential tsunami hazard in the Gulf of Mexico as the back arc basin to the earthquakes in the Oaxaca region. The 23rd of June 2020 earthquake created a small tsunami in the Pacific Ocean, as was recorded by a small number of tide gauges along this coast of Central America and probably one dark buoy in the Pacific. This movie shows a simulation of this tsunami, and if you look closely, you can see all kinds of interesting features going on in the forearc, including on the continental shelf. But what about this sort of a longer period signal that we can see in the Gulf of Mexico? Is it real, or is it probably an artifact of our simulation models? In order to answer this question, we can take a look at the data recorded by the tide gauges around the Gulf of Mexico. I'm showing these tide gauges by black dots. The green square here in the middle is the single dart station in the Gulf of Mexico, and the earthquake epicenter here is shown by a red star. Now, none of these stations had recorded a signal because obviously it was very, very small, if there was anything, well below the detection threshold of all of them, except there is a suspicious signal recorded at Calcasieu, Louisiana, which is on the antipodal side of the Gulf of Mexico with respect to the rupture. The signal here is shown in blue, and the red curve is a 5-minute smooth version of that signal, and the green curve is the simulated time series at that location in the tsunami simulation movie that I just showed you. You can see the timing matches between the two signals, and the question is whether or not, again, this is real. Is this really a tsunami signal? The timing matches, but we can't be sure because this is just the one data point, and all kinds of other features can contribute to this, but it's definitely worth pursuing. Now, why is it that we don't really hear about these things ever? The answer is partly because we usually use these things called finite rupture models, as you know, to simulate the tsunamis in order to match the observations, seismic and tsunami observations in the forearc. These are made to just do that, and in effect, they ignore whatever is going on in the back arc. Also, it's really hard to constrain the down dip extent of the rupture in these kind of models, and as a result, you don't really have a good constraint of the back arc deformation. Here, for example, on the right, I have the back arc. I have the finite rupture models for the 2011 Tohoku earthquake from Chuck Ammon's study back in 2011, and the map on the left is the slip magnitude, and the map on the right is depth. Now, the bottom panels are cross sections of these deformation fields along these black transects on the map. And you can immediately see I can be blunt enough to fit a exponential curve to all of this in order to predict what's going on here in the western Japanese coastline. This is not scientifically rigorous because there is not really a good constraint on this. These things are not made for this kind of deduction, but at any rate, it will predict a really small deformation at the depth of 60 kilometers, which would translate in a very, very small surface deformation. If you're going to build a model based on this, you're going to be dealing with a very small tsunami as a result of that. So what about other approaches? We're all familiar with Okada algorithms to calculate surface deformations from buried inclined faults, as I'm showing here in this figure. And you can calculate the surface deformation, but you can immediately impose a level of complexity by adding this landmass, sort of a topography in the middle. And you can, again, immediately see why this is going to cause problem because you are partitioning your oscillation modes into two completely separate domains. The front mode, or the forearc, is going to be affected by the front of the deformation front, whereas the back arc is going to be governed by this displaced volume of water, which is kind of different from what you see in the forearc. So this model is nice. It's a good, nice cartoon, but is it real? Has these things ever been recorded before or documented before? And also, if yes, what are the important factors affecting their properties? Finally, I just mentioned that these two things are different. As a hypothesis, can we show that these things are different by essence? And the answer to the first question is yes. In the aftermath of the 2011, a small tsunami occurred in the Sea of Japan, as is reported by this 2015 Pagioff paper by Mortani et al. And what they did is basically they presented that a really large data set from a wide range of tide gauges all around the Sea of Japan, both on the Japanese side and on the Russian side. And these waves were also observed as small oscillations on the sea level by the local fishermen. And the data sets, the time series from these tide gauges look pretty much like this. You have this high frequency content for a couple of hours that's followed by a longer chunk of oscillation in the rest of the record. Here, I'm trying to fit simulations to these observations to improve the fit of traditional Okada style tsunami simulation by introducing complexities such as surface waves and horizontal component of the bathymetry, because as was done by Murtani et al., because the vertical component is so small. Again, you can see, you can argue that addition of surface waves and local bathymetry is improving the fit of the high frequency, but not by much, and as shown in this correlation coefficient over time. But then you can see after the high frequency thing passes, the longer period is predicted very well. Now, what are the important factors affecting these things? Well, let's go back to the Calcasieu example that I showed before. And in order to mimic this situation here, we can use this simple numerical experiment. I have deep bathymetry surrounded by shallower bathymetry, and everything is encased by land here. Now I can simulate a tsunami using hydrodynamic methods and ray tracing from a half cylinder here in the south. And the hydrodynamic simulation immediately shows you that there is this little bump here in the antipode. And there are other things, of course, as maximum modes of edge waves. But then the ray tracing shows you that everything other than a direct hit, perpendicular hit, is going to be diverged by this deep water region as a diverging lens. And again, I can do better. I can use a rectangular source, and a rectangular source, what it gives you again is a dominant large amplitude here in the antipode. Now, this is the effect of bathymetry. But if you look closely again at this map on the left, you can see that Calcasieu here is located at the center of a concave coastline. And you can approximate any concave coastline as a part of a really large geographic circle. By decreasing the radius of that circle, you can increase the curvature of the coastline, which is exactly what I'm showing here in this little cartoon. This is a deep, flat ocean with a narrow continental shelf, shallow continental shelf next to the coastline, and I'm increasing the curvature by reducing the radius. And at each step, I can simulate the tsunami from this rupture that I've designed here. And here is what I get. The vertical bars here at the coastline are coastal tsunami amplitudes. And you can see as I'm increasing the curvature, I'm also increasing the tsunami amplitudes in the center, which is a result of constructive, again, edge waves getting focused in the center. So bathymetry and more coastal morphology affect what we see in a back arc and best candidates in a back arc. What about the source? Well, it's a little bit more complicated, but we can do a whole bunch of, again, simple numerical experiments here. I have a flat back arc, and all of these panels, I have flat back arcs separated from the deeper forearc by this narrow spit of land. And then I'm permuting over all kinds of source parameters, magnitude, depth, and focal geometry to simulate tsunamis in the back arc from Okada style solutions. And what I get is kind of interesting, because we all know that in a forearc, the dominant period of the tsunami signal is uniquely determined by the fault width, and this is textbook. But in the back arc, it seems that it's actually a function of fault depth. In other words, these are measured from my simulations, numerical simulations, and I have just measured the dominant period of the oscillations in the back arc as a function of dip. And again, this green curve is a fit to those data. Now, this is a quadratic fit, and you start wondering why this should be the case. Well, if you think back about what I showed you before about the little cartoon here, I argued that it's the volume of this water, displaced water, that's going to affect the tsunami simulation in the back arc. without the direct effect of the front of the rupture. And then and this little sketch shows that the surface projection of the tsunami, of the deformation, is actually going to be changed by the dip angle. In other words, the change in dip angle changes this quote unquote effective length of the deformation front in the back arc. And this is exactly what I can see here. My model predicts by this by these single circles and this red curve. This is the change in the dominant period predicted by the changes of the effective length from my Okada solutions. And the two things, both of them have quadratic fits, and they predict changes as a function of changes in dominant period as a function of changes in depth. Now, let's move on to Oaxaca. In order to simulate tsunamis in the back arc, I would need some information about the seismicity of the region. These are, in fact, CMT solutions of the earthquakes in the CMT dataset, and they are color-coded here in this map according to focal depth. The deeper, the shallower part are here, and as you move away, away from the trench, you're producing a nice Benioff zone. Here on the right, I'm using the idea of Cliff Rollix angles in order to make this ternary diagram. And this, what it does, it basically decomposes the focal geometries for all of these events into three flavors: and strike slip, thrust, and normal. And if I remove the deeper events, I end up with this sort of a scheme that tells me that the region is predominantly in the flavor of thrust events. Now I can sort of make a histogram of the azimuth of the strike angles of all of these earthquakes, and they're beautifully clustered around 280 something degrees, which is roughly the azimuth of the trench. And the dip angles are clustered around about 30 degrees, which tells me that large earthquakes can also occur at large dips. They don't really need to be super mega thrust at really shallow dips. In order to find a sort of a dominant mechanism, I use the smallest scatter of Kagan angles, and I get this sort of mechanism. I'm just forcing a dip of 40 degrees in order to get the largest tsunami amplitudes in the back arc. As I just showed you, that larger dip angles result in larger tsunami amplitudes. And this 40 degrees is sort of a top limit of what you can get from a mega thrust earthquake. And then using a simple slab 2 model here, I'm getting a flavor of what the slab here looks like, and the colored parts correspond to the dips between 0 and about 50 kilometers of the slab, which can host these kind of events. And then I'm making just fake earthquakes, making up earthquakes in these flat parts using the dominant mechanism that I just showed. Obviously, this is just an approximation. And for each of these single events, I can simulate tsunamis in the back arc region in the Gulf of Mexico, which is exactly what I'm doing here. This map is a map of maximum tsunami amplitudes for each of these scenarios. And the vertical arrows around the Gulf of Mexico are coastal tsunami amplitudes from these tsunamis, from these sources. The green star here is the location of this past June's Oaxaca earthquake. And again, you can immediately see that the largest tsunami amplitudes are in Calcasieu in Louisiana in the north, and of course in Coatzacoalcos in Mexico as the main rupture front. Now, again, the favored position to generate large tsunamis in the Gulf of Mexico would be around Oaxaca. In a final analysis, back arc tsunamis can create considerable waves. We just showed that, and the earthquake magnitude and the dip angle of the fault plane are the most influential source parameters in the back arc tsunamis. Generally, larger dip angles create larger back arc tsunamis. The usually secondary factors, which we consider to be second order, which are horizontal displacement and the Rayleigh waves, contribute to the higher frequency part of the back arc tsunamis. And finally, earthquakes in Oaxaca tsunamis. About Oaxaca tsunamis, earthquakes in Oaxaca region are the most likely candidates to create largest tsunamis in the back arc Gulf of Mexico, and geometrical distribution of energy as well as the effects of focusing edge waves would result in the largest tsunami amplitudes in Coatzacoalcos and Louisiana in the US. Thank you.